Hello, everybody. This is our weekly paper, and it's by Kyle Young and colleagues called Fisheries-Induced Evolution of Alternative Male Life History Tactics in Coho Salmon. Right, this paper addresses the idea again that fisheries harvest can cause artificial selection on the population you're harvesting. And this is an ongoing problem in all fisheries of the world. Generally, fisheries harvest reduces the fitness of the fish who are caught. Obviously, if these fish happen to be larger than the fish that are not caught, then that's by definition selection against large fish. So commercial fish populations are evolving to be smaller everywhere in the world because of fisheries-induced selection against larger fish. Just parenthetically, it's not actually quite that simple because some fisheries regulate the size of the fish you take, and in some cases there are minimum limits, and in other cases there are maximum limits. But in most cases, the net selection seems to be inevitably against large fish. This selection not only can affect the sexual system, as we saw last week, but it can also affect the mating system or the pattern of matings between males and females, even if it doesn't affect the sexual system. So fisheries-induced selection can influence more than just the size, but also the mating behavior and the mating system. And this paper is an example of the possibility of this happening in a species of Pacific salmon called coho. We don't have salmon in the Mediterranean naturally, but of course you can buy salmon in the restaurants. And a lot of people consider salmon to be the best, absolutely the best eating fish in the world, especially if you're from the Pacific, because it's so rich. It's so firm and it's rich. And so it's a major commercial species, and therefore is receiving major fisheries-induced selection. So right now I'm just going to summarize the salmon life history briefly in the mating system and the mechanism by which fisheries-induced evolution of the mating system can occur, so that you can understand the details of this paper as you read through it. So salmon spawn in the gravel in small freshwater streams. And then they live in the freshwater system from the rivers down into the estuary for about a year and a half until they're big enough and strong enough to make it out in the ocean. Then they osmoregulate and migrate into the ocean, where they spend another year and a half, after which they mature and then migrate back to the exact same stream that they spawned in, and they navigate back by the sense of smell. All right, in male salmon, there are two mating strategies, the hook nose and the jack strategy. And the hook nose is the common strategy in most natural populations. And in harvested populations, the hook nose is becoming rarer and rarer and is being replaced by the jack strategy, which is a strategy that resembles females. So this is the sneaker male strategy. This male is able to fool the hook nose into thinking that it's a female. So the hook nose male is a larger one, and it's aggressive and it's competitive, and it fights against other males for access to the spawning females, and which presumably increases its mating success with spawning females. And the jack strategy is just to impersonate a female, get up close to a female, while the hook nose is off fighting somebody else, and then just fertilize the eggs of the female without the hook nose noticing. So a common observation in commercially harvested salmon stocks is if a stock is targeted with intensive harvest, then the hook nose strategy becomes rare and is replaced by the jack strategy in males. And in stocks that are not harvested, the hook nose strategy is ubiquitous and the jack strategy is quite rare, usually. So the hypothesis is that this effect is caused by harvest because the jack and hook nose strategies have some genetic basis, are heritable, and fisheries harvest represents selection against the hook nose males because they're larger. And size variation has a heritable genetic component. So if you're selecting against large size, then you're selecting against genes responsible for large size. All right, so I just want to go over the life history in more detail so you can understand. It's a little bit complicated, the model that's being used in this paper to help us understand this idea that's being presented that fisheries-induced selection is causing evolution towards the jack mating history in males. Okay, we're looking at figure 2 right here. I'm just going to go over figure 2, help you understand what's going on here. So part A of figure 2. All right, so this represents the two pathways to hook, nose, and jack, and this is time or age on the x-axis and body size on the y-axis. So this shows that you spawn at age 0, and then you go through this 1.5 years in the freshwater, and then by this critical age right here, just under 1 year, a decision is made. In every male, a decision is made whether it's going to be a hook nose or whether it's going to be a jack. So there's this critical age stage right here, S sub A. That's the critical age at which the decision is made. And what this graph shows is that males that are a little bit bigger at this critical age, this is log of body size. So if you're a little bit higher on the y-axis, if you're a little bit bigger at this critical age, if you're a little bit bigger, you develop into the jack. If you're a little bit smaller at this critical age, you develop into hook nose. So the hook nose stays in the water a bit longer than the jack, in the marine environment. So at age about 1.5, both move into the marine environment, and the hook nose stays in until age 3, at which point it migrates back into the freshwater streams to spawn, whereas the jack migrates back in at about age 2 to spawn. So this graph shows that there's a trigger at a critical age, a developmental trigger that tells the fish which road is going down, either jack or hook nose, and that trigger is determined by the size of the fish. If it's bigger, the trigger is towards the jack. If the size is smaller at this critical age, the trigger is towards the hook nose. Okay, and the other crucial piece of information in this graph is this S sub C. What is that? Well, this represents the threshold in size above which the fish will develop into a jack at this critical age. So when a fish reaches this critical age, either it's above the threshold or it's below the threshold. Every fish is either above or below the threshold at this critical age. So at this critical age, every fish either goes down this path or this path based on whether or not it's above the threshold. Okay, so there's two criteria that determine whether it's above the threshold. Number one, the size of the fish. And number two, what that threshold size actually is. And what that threshold size actually is this little variable here, SC. And what that threshold size is different in different fish. And in this model assumes that that threshold size has a genetic component. So some fish have a threshold size, have genes that say its threshold size is quite small. So some fish might evolve into the jack when they're down here. In other words, the threshold size might be down here. And they'd have to be even smaller to develop into the hook nose. In other fish, the threshold size might be way up here. And so you have to exceed this threshold size to develop into a jack. And anything below that, they're going to be a hook nose. Okay, so it's a little bit complicated. For any fish, there's a threshold size. But each fish has a different threshold size because each fish is genetically different, has different genes to decide what his threshold size is. Okay, so that's the model. Okay, so let's look at part B. So this shows it a little bit schematically here. So here on the x-axis, you have the condition, in other words, the size of the fish at the critical age. So if the size is greater, it is a jack. If the size is smaller, it's a hooknose. Okay, but there's this area in between where it's ambiguous. It's not clear just from the size what the fish is going to be. And this area where it's ambiguous, what determines what the fish is going to be is these genes that tell the fish what the threshold is. So if it has the genes that say the threshold is right here, then this is going to be the cutoff point. And you're going to be a jack above and hook nose below. If your genes tell you that the threshold is here, then this is the cutoff point. You're going to be a hook nose below that and a jack above that. All right, so this little figure shows that both of these have normal distributions. So the fish size has this normal distribution. Okay, so the mean size of the male at this critical age is right here, but some of them are lower than that, and some of them are higher than that. Okay, so the ones that are over in this direction, the larger size at the critical age, tend to become jacks, and the ones that are the smaller size at the critical age tend to become hook nose. And also, the genes that determine what the threshold is also follow a normal distribution. So most of the males have this threshold. Some of the males have this threshold. Some of the males have this threshold. Okay, and that's the idea is that this is genetically determined, what the threshold is. So if your threshold is way over here, then if you're above this size, you're going to be a jack. So most individuals are going to be a jack, which is why it says jack down here. If your threshold is down here, then you're going to be a jack. Most individuals will be a jack. Whereas if your threshold is up here, then most individuals are going to be below the threshold, and therefore they're going to be a hook nose. So that's why the word hook nose is here. All right, so here is sort of a diagrammatic depiction of how fisheries-induced evolution can occur as a result of selection, either on condition or on the genes that determine the threshold. So the x-axis is basically the size at the critical age of males, and the y-axis is the genes that determine the threshold. Okay, so if your threshold genes say that your threshold is very low, then most individuals are going to be jacks. So you're over here, and most individuals are going to have conditions that exceed the threshold, so they're going to be in the jack area of the curve. If your condition genes set your threshold very high, then most individuals are not going to be big enough to meet that threshold, so most of them are going to be hook nose in this portion of the graph. All right, so where are the natural populations? Where most of the natural populations are in this area. The condition is fairly small at the critical age, and the threshold is mostly larger than that. So the vast majority of fish then are hook nose in natural populations. Though in a few cases, the threshold for the switch is quite low in natural populations, and in those cases, you're going to be in the jack portion. Okay. Hatchery populations are up here. So hatchery populations can basically decide what kind of fish they want. So hatchery populations have selected for fish with a very high size threshold, determining what the mating system is, and also fish that are very big. All right, so in hatchery populations, most males are hook-nosed because the threshold genes are very high. And even though the fish are big at the critical age, they're not big enough to exceed the threshold most of the time. So the majority of the males are hook-nosed here in the hatchery populations. So we can imagine a harvested population right here occupying this oval for these conditions and these threshold genes. Okay, so the fish on this side of the line are jacks, and the fish on this side of the line are hook-nosed. So this is the region of phenotype space that the population occupies, gives some proportion of jacks. All right, now this population is harvested, and it can be pushed towards the jack portion of the curve on either dimension. It can be pushed towards this portion of the curve on the x direction, that's increasing the condition at the critical age, and it can be pushed towards the jack portion of the curve along the y-axis. If you're reducing the threshold for switching over to jack, and then you're pulling it down on this graph. So either type of selection will move it towards greater jack mating systems. So how could selection move it to the right? Well, if you're selecting against those large males, then you're selecting against the hook-nose phenotype, because you're selecting against those large males. And if you're selecting against the hook-nose phenotype, then you're selecting against individuals who are small at the critical age, because those are the hook noses. So you're selecting in favor of individuals that are larger at the critical age, and larger at the critical age is to the right on this graph. And if there's any heritability of size at the critical age, then this selection will result in evolution. In other words, genetic change in the population. Similarly, if you're selecting against the large hook-nosed males, then you're selecting against males who have the genes for a high threshold for transition, because those hook-nosed will tend to have genes with a higher threshold, so you're selecting against those genes. So as a result, you're selecting in favor of genes with a lower threshold for transition into a jack. So you're pushing the population vertically down on this diagram. Okay, that's a quick introduction to the logic of this paper, so you can understand it a bit better as you read through it. So enjoy. We'll see you next time.